Hi, I welcome everybody here. Today we'll talk about hardware implementation of my model that I designed, and then I tried to implement it in hardware. And in future, hopefully, if that works good, we will be designing the um, chip as well, an electronic chip, system on chip SoC. So this hardware implementation we will do because in the previous videos we spoke about the software model design for spacecrafts, for NASA, and for Boeing, for aviation, and we did a comparative study and model how we modeled our physics informed neural network with that of the uh, uh, space and the earth-based systems as well. So let's begin our journey here with the hardware implementation, how we did with the hardware. So let's talk about it one by one and see what we got in here. Um, so the previous model that we discussed before, in that we took help from some of the reference papers and the books, and for the compilation and for the studies of this hardware implementation, I took help from these IEEE research papers, which are very recent papers. They are not very old papers within last 5 years or so. And then the NASA's technical documents. I studied some of the sections which are used in this page number as I'm showing here. This is related to the document that I prepared, and it is telling the page numbers and the sections there. Then the technical document of Canadian State Space Agency as well. Then the Boeing, the Canadian Space Agency, and then the Boeing and Lockheed Martin's publication we discussed here. It tells about the sections and the page numbers. Then some of the books I consulted, I took references, and which are mentioned in the in sections and page number of my report. Now, this is a clear picture of the hardware design. We will talk about various sections. If you look at it, where the cursor is, this is the computing unit. This is my laptop where I programmed everything and how this is connected with various other components. This is a one unit is the computing. I will talk about all the components in this computing unit and how we do the interconnections. We connected, not really connected at so far physically, but this is a design module. Of course, when we will be doing it practically, we probably will have issues doing it, but this is a design pattern. So the next in the computing unit, what we are doing is we implemented our model, physics informed neural network model predictive control here in the laptop. So there is a file IPYNB, how that is changed into another format, and then it is sent to various other units in the computing section. And what the second section is the sensors and the measurement sections, where we will take help. We will take the input data from the measurement unit, for example, voltage, current, temperature, uh, vibrations, GPS, and all that. For the aviation and space, we will take data from the solar, the radiance of the sun, from and the temperature, the thermal effects, the vibration effects, the GPS location of our spacecraft or the aircraft, and all that data will be taken from the sensors and the measurement units. And then the sensors and measurement unit is here, and then we talk about the app, what this will do. So after doing all the processing of the data we have and getting the input data for the physics informed neural network, I will mention here again that for my algorithm, that is a combination or a study of the three different things. One is the physics informed neural network, physics informed architecture, physics informed data. That depends upon the um, specifications of the various components and the physical environment. Say that is the laws we have to follow, the universal laws like Faraday's Kirchhoff law, Ohm's law, and the laws related to the aviation and the space. Physical laws, the pitching and yawing angles, the rolling and banking of the aircraft or the in space, its latitude, its longitudes, its altitude, its pressure, temperature, all those sensors. So that is, and we have to abide by the physics laws. So one is the data where we talk about the physics laws, and then the another is we select a boundary that it has to be within that boundary, and the third is the actual data, real time data that we are getting. So we will do that computation here, and the actual data will be from this, and then it will take an action, and will perform something like it will run some motor actuator, some other thing to rectify, to forecast or optimize the system. Then the data will be further processed, and we will see. Let me just make the slide a bit bigger. Then the data acquisition and signal sections, where because it's a lot of movements between AC and DC, digital analog signals. Sometimes we change it. Then we have a unit where we will debug. We will do a debugging and visualization and monitoring. Then we will also be logging the data somewhere. So we have to do a data log, and then we will be having eventually a monitoring system where we can see what is happening. Are we close to our results? So here for the next, I will just mention some of the industrial and academic research gaps related to the electrical engineering, which are being studied and addressed in our model, in our hardware implementation. So we will discuss them as well one by one, that what are those issues that we addressed, and which research gaps are there, that we will talk. Say for example, for the NASA's predictive control in deep space with no Earth reliance, because the data, the predictive control we have in deep space, that is one of the issues that NASA is going through, that it has the predictive control in deep space with no Earth reliance. Another is Canadian Space Agencies that regulates thermal loads in satellite under harsh conditions, and there are issues with the regulations of the thermal loads. For the Boeing fuses and EMI, IMU, and fuel data for flight optimization, there are issues that are not 100% addressed and followed, but partially most of the issues that we have addressed and tried to resolve with our algorithm or model. But this is not related to software, and I will not explain software as much as I explained that in the previous videos. For the Airbus, the issue is like it enhances ECS and HVAC via sensor-based predictions. So those are issues. And with Lockheed, and that enables a stealthy closed-loop flight control, and there are more than the Canadian Bombardier. Then these industries and academic research gaps related to electrical engineering, which are studied, but there are also some of the issues with the military grade precision in fault tolerance. For example, Northrop Grumman's that adapts to wind or the altitude with real time thrust control. When the system adapts to wind or the altitude, there is issues with real time thrust control. So for the Raytheon's that issues filters radar jam data using physics constraints. When they are doing the filtration of the radar jam data, because the radar in the system they are jammed, so then the data differs, right? So whatever is being done in a smooth way, when there is a radar jammed, the radar jammed data which may not be available, then when you use the physics constraints, then there are the issues. Then for the general dynamic real-time balancing of load and vibration stress, because load, that the electrical loads I'm talking about, that they those are also because of the mechanical stress and mechanical or vibrational issues as well. So my vibrational stress is there. Then for the Thales fast MPC response to multi-sensor fusion, so because the model predictive control we have designed or mentioned here, let's see if that works with this particular thing, that because with the Thales MPC response to multi-sensor fusion, because there are so many sensors in there, so there is a possibility that your MPC module can respond to various different sensor fusions. Then for saffron, the issue is for the regulation regulates jet engine vibration and pressure dynamically. So one is the pressure, another is the vibration, and that regulates both of them. For the Rolls-Royce that predicts failure via vibration analysis and adaptive output. Uh, because when there is a failure, so it predicts failure with the vibration and analysis and adaptive output. So these are the issues. And for the now, let's do the advanced integration in aerospace and energy. Let's talk about these, like the SpaceX and the Blue Origin and Siemens and Textron, these and General Electric. They are having issues. Let's say, for example, aerospace for the General Electric. Aerospace harmonizes power, temperature, and control systems. This the system is like they're having a harmonization of the power, temperature, and control system. I mean, there is issue with the harmony. For the Honeywell, fuses uncertain sensor data into reliable control loops. So when the data uncertain that sensor data, if it presents somewhere there, so if it is going to the reliable control loops, there are the issues. For the SpaceX, the big huge company, the richest one, that improves rocket landing using adaptive thrust control. So I mean, these are the advanced integration in aerospace and energy that I simply addressed here. For the Siemens, this important dynamically controls power signals in electrical systems. So dynamic control, static control, real-time control. So these are some of the integrations. Now, deployment in global defense and embedded AI benefits. For the Embraer that adapts ECS, electrical and computer science related to cabin pressure for turbulence comfort. For if we talk about Pakistan Air Force integrates radar and actuator control in JF-17. The JF-17 Thunder aircraft they have. The issue that I addressed here is that for Pakistan that integrates radar and actuator control in, because uh, the signals that you are getting from the radar, and especially in the jamming condition, they are different, and the actuator control are not according to as it was behaving before within the framework of the architecture that has been designed for the actuator to work. So whenever there is a jamming, there is some issues in the radar, and then you control the actuator through it, then there is an issue. So what they did is they actually did an integration of the radar and actuator. But the issue I found here is that this is for the desirable situation. So especially for the Air Force, when there is jamming or there is some intruder, something is happening with your data or the input coming to the radar, if something is not proper, is not according to the algorithm being designed, it means the actuators that will take a response or a reaction would not be as as desired. For the India neural path optimization in Tejas fighter, because in India has the Tejas fighter in where they integrated neural path optimization. So it is somewhere close to the model I discussed, but my model is more physics informed neural network. Probably this for the HAL um, uh, in India, that is for the Tejas fighter, they mentioned the neural path optimization. It means whatever the optimization related to electrical energy or the telecommunication or satellite or radar technology or the Indian Air Force Tejas fighter, the system that it has within its framework that takes the neural path optimization. I mean, the reason I'm saying is like I'm just discussing some of the deployment in global defense and embedded AI benefits. Again, DRDO, thermal aware AI control in drones and and the missiles. But the reason I'm telling here is because, as I said before in my previous video, that thermal aware AI integration is very important, which is more addressed in aviation and aerospace. Then for the Turkey predictive mission extension with fuel and sensor feedback. So value proposition physics based AI prevents unrealistic behavior. Why I discuss here in this presentation, physics-based AI prevents unrealistic behavior, because if there are neural networks, there are deep neural optimization forecasting models and physics informed networks as well. But the combination of the physics informed with MPC is like more reliable, that will prevent unrealistic behaviors. Then the filters noisy sensors data and the real time and their we will talk about deployment across AI space and industrial platforms. We'll talk about how this model or this framework reduces fuel and wear costs. Then how it takes care of plug and play with UART and other sensors. So the research gap and how they are addressed in the hardware. There is like the research gap was there was no real-time embedded AI MPC for energy systems loop with live sensor feedback, because in our hardware implementation, where I will discuss about Jetson and Arduino control, we will talk about real-time uh, embedded AI MPC. Edge deployment strategies for PINN MPC missing, plus Jetson deployment outline. I mean, these are some of the, because I have not yet discussed the architecture, so it's just to understand these gaps. It's sometimes it's hard for the non-technical, those who are not related with aviation and space, but still, I mean, we will later on discuss these gaps and how they have been addressed in the model I presented for the hardware implementation. I included filtering and dual path logic and implementation of UART, I2C, SPI, hardware shielding, heat sink, and plug and play, and all. So these are some of the other gaps though. So let me move quickly to the framework for hardware implementation, PIN MPC electrical module, because I don't want to waste more time, because those who have to understand this architecture, it's hard to align it with what deficiencies are there in the previous models. So let me check my slide here. I'm here. Let me check if I'm doing great with the videos and everything. It is being shown here in my presentation. Yes. So it was not working now. So let me go to the slideshow again and see. I can see it with my. Okay, now when we talk about the real architecture, see, as I said, the computing unit is here, the sensor measurement unit, the actuator output interface, debugging that as I briefly explained a little bit. So now, when we talk about embedded hardware stack, you don't have to confuse with the model or type or specification. I will, in the next few slides, I will be telling the purpose and the function of these components. So for right now, I'm talking about this section, computing unit, right? I'm talking. So if you see, I'm talking about Jetson Nano, which is here, right? Then I'm talking about Arduino Mega, which is here, and I'm talking about USB UART, which is here, right? So and now what we are doing is the model that I have in my machine, in my laptop, in my system. I designed it with some algorithms, some mathematics, and tried to implement it in as a software in the Python Google Colab with the Python coding by using all various libraries, functions, mostly physics informed neural networks, some operators, some layers, some TensorFlow, and some of the gradient descent, loss functions, and all that mathematics here. So now it means whatever I have, how that has to be implemented in my computing unit first, how my system will compute. So the data control flow will be like from the sensors, right? From the sensors to uh, to the Jetson and then MPC decision and Arduino actuator. This will be the data flow. So where is the sensor? Sensor is here. From the sensors, it will move on to to the Jetson for here, that I will show it later on, and it will do some model predictive decision, and then the Arduino will take care of the actuation. So this enables physics aware low latency closed loop control and modular and scalable architecture. If you look at this colorful block diagram, this is, you don't have to really focus on this. The reason I'm telling it why we choose this NVIDIA's Jetson, the thing is because it complies with, it works good with the utilization of artificial intelligence modules into hardware implementation. If you look at that, it is for the aerial imaging, it has been used um, for the smart systems, and for the detection, for autonomous robotics, for drones and UAVs. It is being used for edge cameras, for the traffic management systems, for automated inspection. I mean, this is like all in one. There are some others as well, but I chose this. This was, and I'll be doing some prototype in future for on this. So now here is the architecture that I tried to design. So far, the framework has been designed, and let's see the connections. Now, laptop or the PC is used to develop and train the physics informed neural network uh, model, predictive model, which is here in the laptop, right? So it is here. Then the laptop validates and test control logic in the simulation. Then the next is the this validates. How I did it, the validation, I did it by running in the Python in Google Colab. Then USB to UART adapters that bridges communication between the computer and the microcontroller, because uh, if it means I have to join it with through some wires or cables. So what I will do is my next it will be with the Arduino Mega. So what that Arduino Mega will do, Arduino Mega executes trained PIN model for low power edge control, because it means it will shift it to some low power edge control system. Then this Arduino Mega is, then the next is the Jetson Nano that executes heavier pin interface for high resolution decision making. We will further discuss that how this high resolution system, we later on we will talk about it. So it means if you see here, I'm showing here, you have a Jetsons Nano, and the rest, then the Raspberry Pi, and the laptop is connected at Arduino Mega. So from the laptop, it is coming to Arduino Mega, and this Raspberry is there, and it is connected with the Jetson. If you see the components here, NVIDIA's Jetson Nano is looks like this. TX Xavier laptop can be any i9 based system. Arduino Mega, is like this, and this is USB UART being used, and Raspberry Pi 4B. This is here, and this is the whole structure that the laptop where where the software model is. This is connected with this with the USB connected with Arduino, and they are then all interconnected with Jetson and the Raspberry Pi. So because it is not easy to at this moment to understand, but later on we will talk more about the functions and how it works, purpose and the functions. So in this slide we will see the purpose for the laptop. As I said before, that acts as a central development hub where I did my work. So here is the laptop, here is the, this is a physical look, and this is an schematic kind of look. So the purpose is to train physics informed neural pin using simulation data sets that I did, and to develop and tune the model predictive MPC using optimization libraries where that we did in Python, which was integrated with some of the functions and operations. Say for example Eurobeef, say for example Payomo or ONNX, or some of the space related. So I tried to do it with the available most of them, they were available within the Python. So I I I integrated, or I embedded those into the software model. So then it tests the complete control loop virtually before deployment. Of course, with the Python, we test it, we restart it, and the kernel, and we restart and keep checking and finding the errors in it. If there is an error, we redo it, and then the processing that takes lots of time with the huge data. At the moment, I did it with the synthetic data. In future, I will be doing it with the actual data. Then the interface with the hardware to upload firmware and models. This is like laptop does the interface. Then the USB to UART adapter, the purpose is that serves as a combination bridge between the laptop, that is the host, and the microcontroller that is the target. So it means there has to be. So the function of this USB to UART is converts USB signals to a serial UART protocol, because the movement or the bridge is very important to make sure that this is being sent as desired. This enables downloading of trained uh, pin parameters to the edge device, because edge device needs that the data as well, not only the implementation module, because it has to have that data as well. And this facilitates real-time data streaming, telemetry or command. In future you will see how that telemetry and command is important. Then next is the Arduino Mega. If you see, that laptop is connected with USB UART, and then this is connected with Arduino, which is here. Arduino, as I'm showing with the cursor here, and in the schematic it's here. So the Arduino Mega performs as a low power interface of lightweight pin model at the edge. So, and the function is it runs trained pin for simple tasks, for example, voltage regulation or fault flags. So it means whatever has been trained in my model, so uh, now it has to be run. So in order to run it for simple tasks, so this will take care of that, and it controls GPIO based actuator relays, LEDs, simple motors, right? So input, whatever input is being given here from the laptop, and it has the data, it has the results, it has the execution operation, and everything is in here. So from the laptop it goes to Arduino Mega. Now, what Jetson Nano will be doing, which is here, if you see another a connection of the Arduino with the Jetson, I am showing with the cursor here. You see Arduino Mega, it is connected with the Jetson Nano. So now the Jetson Nano executes high resolution real time pin interference and feeds MPC for decision making. So what this guy did, this was for the pin. We will see they will how they will serve in future. For now, this takes care of the physics informed neural network data and everything. But for the actuation, for something to be done according to the model predictive control that is modeled in my algorithm, this take has to take care of that. Jetson Nano is here. And its function is to process complex physics aware predictions, for example, thermal, multi sensor states. So this has to process those complex physics. So this will do it. That runs trained neural model in TensorFlow and PyTorch. As I said, because in my Python that I had in the laptop, in the Google Colab, this goes to the Arduino, and then this will take care of the TensorFlow that has different mathematics, different flow of work, and the PyTorch with libraries and functions. So this will take care of those complex things. So that processes complex physics aware predictions. Then it interfaces with sensors and actuators over something, right? UART and SPI. Then it will take care of the next next step, that it is connected to the as an interface with sensors and actuator. What is actually happening? One is the data that the model I'm giving. This is going to Arduino, then it is going to the Jetson Nano. It is getting data interface from the sensors. This Jetson Nano hosts the on-device MPC optimizer to perform fast control decisions. So whatever has been told in the model according to the data, this has to take some on-device MPC optimizer, so to perform fast control decisions. And this Jetson Nano sends final control command to actuators via microcontroller or GPIO. So if you see, the red one is 5 volt. See, this is connected here. This is here connected. Then ground is with the black one, and the blue one is the UART, which is, you see, USB to UART adapter is here. So that is how they are connected. So overall objective is what? Is to enable the real-time communication and cooperative interference between Jetson Nano, Raspberry Pi, and Arduino Mega with serial monitoring from a laptop using USB to UART adapter. So it means we have to make sure whatever we have designed here in our laptop, that goes, and it serves the objective to enable real-time communication and cooperative interference between what between Jetson Nano, Raspberry Pi, Arduino with a special one. Now, the component connections pin by pin, as I said, Jetson Nano, SDSCL, uh, I2C bus. These connect internally or via sensor networks not shown in this image. I mean, this is not required at how they are connected. Input sensor data, for example, it is temperature, voltage, or IMU. Jetson Nano will take that input data as well. And the output, what output it will give us? This is the input coming in. So the output would be high level pin predictions to UART and the I2C bus. So it will give some high prediction. So whatever is being sent here and with the prediction result, I will get it here. And the power rail for Jetson Nano is 5 volt. As I said, see there is it is running with the 5 volt and supplies regulated power to Adreno Mega and Raspberry Pi. So Adreno Mega is here and Raspberry Pi is here. It is connected. Now, now, so far you must be thinking why I didn't talk about Raspberry. Raspberry does what? That is the ground to command ground. So now we have the Raspberry here. Everything, whenever we have an electrical circuit, of course, it has to be grounded somewhere. So that ensures all devices share a consistent reference voltage. It means that all the reference voltage to all the devices should be consistent, right? So this is again a 5 volt. Shared power rail supports Arduino Mega via pin mode. See, again, if you see this thing is connected uh, with the Arduino Mega, right? Internal GPI I2C, which is not shown, that can exchange data with Jetson or sensors independently. So here it is. So now Arduino Mega pin A4. If you see here, there is a pin A4 SCL I2C serial clock connected to Pi and Jetson bus. If you see this one, this is connected to Arduino Mega and the and this Raspberry Pi, right? This is connected here. This is used to synchronize timing of I2C base sensors or co-processors. Why we have to make sure that is because it should not overlap the data, because the data is at instant number 3 but it's still not operating or taking the previous or the previous data or the previous step. So this is used to synchronize the timing. The pin 4 uh, UAC orange line, if you see, this is the orange line, right? I was talking about. So this was the orange line. The purpose is to trigger event, for example, send prediction complete signals. So whenever there is an event that can trigger that event, and their TXT UART output, if you look at the TXT uh, right here, which is here, uh, UART output TXT line to USB to UART adapter. So this is our another adapter which is here, and the output transmittal serial data, for example, real-time predictions, voltage thresholds to laptop, that will go here. So 5 volts pin receives power from Jetson Pi. Here is the Jetson and the Pi, right? So it will take that receives power. Rail input supplies operating voltage. Input for this is supply or voltage, right? So USB to UART adapter, because we are explaining each and every component. So this is connected to Arduino. Arduino is here. So this USB, as I said, it is connected to here. Ground is shared ground, prevents voltage mismatch. Connected to laptop via USB, as I said here. So input laptop via USB input receive sensor AI predictions from Arduino. So what this Arduino will do will give the predictions, right? So who will get these inputs? USB to UART adapter. Where is that? Which is here. Which is here. It means that input receives the input is that receives sensor AI prediction from the Arduino, right? So this will be USB UART adapters function. Now, what is happening? We have to, these are the 4 units here for my computing unit, the Jetson Nano, Raspberry Pi, Arduino Mega, and the laptop. Let's talk with the laptop. User uploads models, reads logs, adjusts the codes. User, uploads models. Let's say I'm doing an algorithm, I'm uploading the models, real logs and data, and I adjust the code, right? So what, where the output will be sent? Sends to config or monitoring command to Arduino. So this will be from the laptop, will be sent from here to to this guy, to Arduino. Now the Arduino Mega will receive prediction models or the trigger via UART, of course connected via UART. We are not, we, so this will receive prediction model, because where is my prediction model? Prediction model is here. Uh, it's here, right? So it will take that, or it will trigger via UART. Then the output from the Arduino would be controls relays, uh, and the pulse width modulation log data transmits to laptop. So it will give to the laptop. So for the Raspberry, optionally collects telemetry or provides power. I mean, it's not all the time. If there is a need, then we take care of the Raspberry. And what Raspberry will give could relay commands or data to the Jetson Arduino. So Jetson and Arduino. So this will, whenever there is optional telemetry data, that then it will work. It will give to Arduino and the Jetson. Now the Jetson Nano sensor data, Python interface code. So physics informed predictions to Arduino via this. So what it will give, a physics informed neural network, Jetson will give it to the neural. I mean, they are all interconnected somewhere. They are communicating, talking to each other. Now the purpose and how it connects and interacts, as I said, laptop, workstation, USB, UART, SPI, Arduino Mega, Raspberry, uh, Pi 4B, and NVIDIA's Jetson Nano. Purpose, as I mentioned before, this is again the next slide, almost the same what I explained before. Now, development phase, digital series, laptop generates train pin. This is the work I did, right? Laptop. This is what so far we did it in the software, and these are the steps that I'm mentioning here, but those are practically not being done yet. So laptop generates train pin and MPC models, typically ONNX or .pth, using Python, PyTorch. And okay, what is happening actually? The laptop, what I have, the my file is IPYNB, Jupyter notebooks. So if that has to be uh, generated or converted, so that generated trained model, which will be ONNX, this is the format of the file, or .pth, right? They're using Python. So so there will be PyTorch, Cas ADI, or the Jacko, right? So through USB to UART adapter, these files or serials commands are transferred to the Arduino STM. So I'm talking about this thing, right? And these are the sensors, voltage, current, and all that. So voltage level, as I said, will be this, and the constraints is the if Jetson and Arduino differ in logic level, right? One is, let's say, 3.3 volt, another is 5 volts. Use a logic level shifter to prevent damage. So then there is an issue. Now, smart grid sensors. So for this particular, we will talk about how these smart grid sensors, they and its physics is informed, how we implement it in the hardware. So far, I discussed the computing unit, right? The computing unit that I mentioned here. This was my computing unit. So far, I mentioned only this where the cursor is. I mentioned only this. So in next videos, because video is too long, we will be talking more in detail about the smart grids, power flow system, physics equations for all sensors. We will talk about PINN model sensors for military aircraft, equations and sensors, and we will give examples of those aircraft. We will talk about physical equation and sensor inputs. We will talk about commercial aircraft, physics equations and sensors input. Then we will talk about how we connect these measurement sensor units with our system and power supply, how they are being the power supply is being given to this. We will talk about all these sensors with giving to my PIN model, and how then the next stage will be model predictive control. We'll talk about types of sensors in the aviation industry. Then again every time we will discuss something, then we will come back to our main architecture, which is here. Then we will talk about mission critical high speed feedback inputs and giving to my PIN MPC model, then the computational unit, how it's going to work in the hardware. We'll talk about inputs of the spacecraft. We'll talk about UAVs and drones. We will talk about mission critical and high speed feedback inputs. Then we will again come back to our architecture for power supply. For we will discuss solar panels. We will discuss voltage regulators, buck converters, which is being used here for the hardware implementation. We'll talk about the features, the purpose, the functions, the inputs and outputs to these power management and power supply units. We'll talk about computing units. We'll talk about power energy component, sensor measurements, each and everything details and how it is needed, why it is needed for my model, how we implement it. We'll talk about the relay modules, actuators. Then the next step is actuator, the response, right? Device to device protocol flow and how they interact with each other. We'll talk again. Then we'll come back to our architecture, where we will have the computing unit that I discussed. This is which is I'm showing with my cursor. So okay, we so far in this video we spoke about this section only. So we will talk about voltage regulator, solar panel, batteries, power, how this the next section is attached to it. So one section so we discuss in this video so far is the this one that I'm showing with the cursor here, the computing unit. Then sensors unit in next videos we will talk about actuators, interface communication modules and data acquisition, displays and all that. So in next video we will talk more about utilization of all these, and this is it for now. This is our architecture of hardware, and in next video we will talk more in detail about it. Thanks for being with me. Thank you.